what we are given is that write the differential equation of motion for the system shown. So we need to write the differential equation for this system, and then we need to find out the natural frequency of damped oscillation. So part B is, that is, we need to calculate is omega d, and the critical damping coefficient. So the part C will be to calculate Cc here. Okay, so to write the differential equation of motion, for this case we need to draw the free body diagram. So if we give this system some sort of angular deformation, so the theta is here positive in this direction, and velocity, angular velocity and angular acceleration is also in this direction here. Now the mass is attached here, and the spring and the dampers are also attached here. So the spring force is going to be kx, and the damper force is cx dot. Now we know that this is x here, and we are taking x here. So we know that this x is a, which is the distance from here to here. So a sine theta, and this will be b sine theta. Okay, now again, because the angle is very small, so we can take this sine theta equal to theta. So the spring force will become equal to kx, which will become kb theta, and the damper force, which will become kd, and it will become cx dot, or it will become equal to ca theta dot. Okay, so because it's x dot will become a theta dot. So these are the forces that we have here. Now we can write the equation of motion by just using the Newton's second law, that is summation of all the forces equal to ma. So in rotary motion we will write summation of all the moments about O equal I naught, which is IO theta double dot. Okay, now we have two forces here. One is cx dot, one is kx, and the direction of the moments which these forces will create is opposite to theta double dot. So that's why we will have minus cx dot, or and then the distance, or the vertical distance between the O and this force here, which is this distance here, and which is a cos theta, and then you have kx and b cos theta, and equal to I naught. So I naught in this case is the second moment of mass, which is ma square and theta double dot. Okay, now we can put the value of x dot and x, and the angle is small, so the cos theta will be just equal to 1. So what we will get is c a square theta dot minus k b square theta, and then it will be equal to ma square theta double dot. We can rearrange this equation. So what we will get is ma square theta double dot plus ca square theta dot plus kb square theta equal 0. Okay, now if we compare this equation, okay, so the first thing is, this is our unknown differential equation. So this is part A of the solution. Now if you compare this solution with the standard solution that we have, which is theta or x double dot plus 2 zeta omega n x dot plus omega n square x equals 0. So we can simplify equation A a little bit. Okay, so we will simplify this is theta double dot and then plus c divided by m. If you divide this equation by ma square, so c by m theta dot, and plus k divided by m b square by a square theta equals 0. So if we compare this equation with this equation here, so what we having is omega n. So in this case, omega n is with x, and here k by m b square by a square is with theta. So what we will have is km b square by a square. So this is omega n. So from here we will be able to calculate omega n, which is a divided by b, or b divided by a. Okay, b divided by a and k by m. So this is the value of omega n here. Now we also know that we can compare these two terms. So it is here c by m, and here we have 2 zeta omega n. So we can compare these two terms here. So 2 zeta omega n is equal to c by m. So from here we can calculate zeta, which will become 2 divided by 2 zeta guys. So this will become 2 c divided by 2m omega n here. Okay, now in this equation we can put the value of so we can put the value of this omega n, so which will become c divided by 2m, and instead of omega n we will put the value by b by a k divided by m. So if we simplify this equation, it will become ac 2b mk under the root. So this is the equation for the zeta. Now obviously we need to calculate this cc. So for cc, the zeta is equal to 1 because this is a coefficient of critical damping. So if zeta is equal to 1, we can say that this a and this will become cc 2b mk equal 1. So then from here we can calculate cc, which will be 2b mk under the root and divided by a. So this is the value of the critical damping coefficient. Now the part b is actually we need to calculate this omega d. So this is our part c. Part b is to calculate omega d, and we know that omega d is omega n and 1 minus zeta square. So we know the value of omega n, which is this value here. We know the value of zeta, which is this value here. So you can put the values there. So that will become b by a, k divided by m under the root, and inside the square root you have 1 minus zeta is equal to, so this will become a square c square divided by 4b square mk. And if you simplify this equation, it will become k divided by m b by a whole square minus c divided by 2m whole square under the root.